The IEEE does define the 802.11 core standard, 802.11b, 802.11a standard, which uses the UNII bands, and 802.11g, which, like .11 and .11b, will use, of course, the ISM bands. All of these standards have been fully implemented by the IEEE and do specify different capabilities for wireless networking. Now, it is a good idea that you have a very detailed understanding of each one of these standards that have been set forth by the IEEE so that you know exactly what to choose when you are specifying how your wireless LAN is going to function. And the first of these standards is 802.11. This is the first standard that describes the operation of wireless LANs that was ever set forth by the IEEE. This standard contained all of the available transmission technologies, including direct sequence spread spectrum, frequency hopping spread spectrum, and infrared technology as well. The 802.11 standard does describe DSSS systems that operate at 1 megabits and 2 megabits per second only, however. And what this means is that because it's specifying 1 megabits and 2 megabits only, that if we have anything that operates at any higher speeds, they're not considered to be 802.11 compliant. Now, there are other 802.11 standards, like the B standard, that can operate at 1, 2, and 11 megabits, along with 5.5 megabits. It is able to be backward compatible with 802.11 just because it supports the 1 megabit and 2 megabit transmission rates. Now, keep in mind that 802.11 is one of the two standards that actually describe the operation of frequency hopping wireless LAN systems. If a wireless LAN administrator encounters a frequency hopping system, it's likely to be either 802.11 pure compliant or what's known as an open air compliant system, which is another standards organization that develops wireless standards. The 802.11 standard describes the use of frequency hopping systems at only 1 and 2 megabits per second. So keep in mind that even though there are other proprietary systems out there that may operate at 3 to 10 megabits per second with frequency hopping, just like with DSSS, 802.11 is only compliant in the 1 and 2 megabit modes. The standard, which is probably one of the most popular standards ever introduced by the IEEE, is the IEEE 802.11b. Now, even though the 802.11 straight standard was very successful in allowing DSSS and frequency hopping systems to interoperate, the technology definitely outgrew the standard. So soon after 802.11, DSSS wireless LANs were exchanging up to 11 megabits per second. And what that meant was that people were pushing this technology to its limit before there was even a standard out there. So without a standard to really guide the operation of these devices, there came to be a lot of problems with interoperability and implementation. The manufacturers were able to iron out most of the implementation problems. So really, the job of the IEEE became relatively easy overall. Just simply create a standard that complied with the general operation of wireless LANs that were then on the market. Not uncommon for standards to follow the technology in this way, particularly where technology is evolving quickly. And that's exactly what happened with the 802.11b standard. 802.11b is referred to as high rate and Wi-Fi. And this specifies direct sequencing systems that operate at 1, 2, 5.5, and 11 megabits per second. The 802.11b standard does not describe any frequency hopping systems at all. And 802.11b compliant devices are also 802.11 compliant by default because they support the 1 and 2 megabit frequency ranges. Because they support the 1 and 2 megabit data rates, and that's the reason why they're compatible. The high data rate of 802.11 compliant devices is the result of using a different coding technique. Though the system is still direct sequencing, the way the chips are coded, along with the way the information is modulated, allows for much greater amounts of data to be transferred in the exact same time frame as it was with 802.11. 802.11b compliant devices operate only in the 2.4 gigahertz ISM band between 2.4 and 2.4835 gigahertz, and that's what the standard identifies. Now, in this particular case, 802.11b was great because we only had 802.11 to really compare it to, with 1 meg and 2 megabyte for data rates. However, we needed to move this standard along a little bit so that we could actually get faster. And that's where 802.11a comes in. 802.11a is a standard that's actually more recent than the 802.11b standard, and it describes wireless LAN devices in operation of the 5 gigahertz UNII bands. Now, operation in these bands automatically makes the 802.11a devices incompatible with all other devices that comply with other series of 802.11 standards. So this is somewhat of a standalone operation here. The reason for this is very simple. Systems using 5 gigahertz frequencies will not communicate with systems using 2.4 gigahertz frequencies. And that's really how it goes. So 802.11a is mutually exclusive to every other standard that we have for wireless networking. Now, using the UNII bands, most devices with 802.11a are able to achieve data rates of 6, 9, 12, 18, 24, 36, 48, and 54 megabits per second. Some of the devices employing UNII bands have actually achieved data rates of 108 megabits per second by using proprietary technology such as rate doubling, but this is proprietary. The highest rates of some of these devices are just the result of newer technologies that are not specified by the 802.11a standard. So be very careful with these types of things because they are proprietary. 802.11a standard, however, specifies only data rates of 6, 12, 24, and 54 of all of these choices that we have. And that's what the IEEE sets forth. A wireless LAN device must support at least these data rates in the UNII bands in order to be fully 802.11a compliant. The maximum data rate that's supported by IEEE's standard is set at 54 megabits hard-coded. There's also something that's very important about 802.11a. It uses what is known as orthogonal frequency division multiplexing, or OFDM. The 802.11a standard specifies the use of the OFDM technology as set forth by the IEEE. And this is actually the secret behind how this particular standard gets up to 54 megabits per second. OFDM creates 8 non-overlapping channels that are 20 megahertz wide across the 2 lower bands of the UNII 5 gigahertz band itself. Each of these 8 channels is subdivided into 52 subcarriers, each approximately 300 kilohertz wide. Each subcarrier is transmitted in parallel, meaning that they are sent and received simultaneously. A receiving station can then process these 52 incoming signals, each one representing a fraction of the total data transmitted, and then it'll make up the complete transmission. So due to the large amount of information being transmitted at such a high rate, some means of error correction was actually required. As such, they developed what is known as forward error correction, or FEC, and this was actually added to the 802.11a standard by the IEEE. And essentially what it does is just simply send 2 copies of the information in every transmission, a primary copy and a secondary copy. If the primary transmission is lost or damaged, the receiving station can recreate the lost data by running the secondary transmission through a set of algorithms. And this sounds an awful lot like RAID disks, as we're actually sending part of our data right across a stripe across multiple disks and then calculating a secondary calculation with parity. Same kind of thing with 802.11a. With the performance impact being fairly negligible due to the high data rate, it does give us a backup of the transmission, and that's what allows the error correction to work at such a high rate of data transfer. But there is still the problem. 802.11a, not compliant at all with any other 802.11 standard. So what do? Well, that's where 802.11g comes in. This is very similar to 802.11a, but it's designed to be backward compatible with 802.11b. How does it do it? Well, it provides the same maximum speed that we see with 802.11a, coupled with the backward compatibility. The backward compatibility actually makes your job of upgrading devices that are previously compatible with 802.11b a lot less expensive because 802.11g automatically operates in the 2.4 gigahertz ISM band, and that makes them compatible. Now we're dealing with the exact same frequency ranges for 802.11g as we were with 802.11b. To achieve the higher data rates, however, that are found in the 802.11a, 802.11g devices utilize also the OFDM modulation technologies. And these devices can automatically switch to the other modulation which is used by 802.11b, which is called DQ-PSK. This is the modulation which is used for compatibility. And this, of course, will slow down the transmission rate to a maximum of 11 megabits. But still, All the while, 802.11g uses the 2.4 gigahertz ISM band for maximum compatibility. One stipulation here, if you're going to be using 802.11g, it is backward